Okay, we are going to talk about 8.8 improper integrals. I'm going to give a short review before we start solving some problems. Infinite limits of integration. In this section, we are going to see some integrals with infinite limits. And the way we are going to solve them, find them, is summarized in this definition. Integrals with infinite limits means either one of the limits or both of them are infinite. So if this is the case, we have we call this improper integrals of type 1. If you want to evaluate that, you have to use the limit definition here. For the part that goes to infinity, you're going to let that you're going to define a letter b for it, and you're going to let b goes to infinity. First, you're going to find this integral inside, and then you're going to take the limit afterwards. If the bottom part is going to negative infinity, then you're going to let a go to negative infinity, and then find this finite limit first. If both of them are going to infinity, then you're going to separate it into two and apply for each case step 1 and step 2, and then you're gonna get it. Now, another important thing here is the convergence. So we are gonna say such improper integral is convergent if this limit exists. Same here, but if the situation is like this, if you have two infinite limits here like that, you're gonna separate it into two. Then if at least one of them does not have a finite value, then this is divergent. If both of them have finite value, then this integral is convergent. This is what we pay attention to. Let's continue. So there are some examples here. I'm gonna skip those examples. Let me see. Okay, this is a very well-known example, which is the integral from 1 to infinity dx x to the p. Very standard, and we are going to use it when we compare integrals with this to determine the convergency. So 1 to infinity dx over x to the p is going to be, depending on p, if p is greater than 1, it's going to take a finite value. If p is less than 1, then it's going to take an infinite value. That's what we can say about this integral. So p being less than 1 is not good. P being greater than 1 is good for such integrals. This is important, as I said. Second type is integrals with vertical asymptotes. This is called type 2. Okay, what does it mean? You're going to have a continuous function on the interval, but there's going to be a point that it's going to be discontinuous. I mean, on one end it's going to be discontinuous, or inside it's going to be discontinuous. The first one shows when this function is continuous everywhere except one of the endpoints. This is number 2 is it's discontinuous. Number 1 is discontinuous at a, which is the bottom limit. Then the integral is going to be it can be written in terms of limits. We are going to let c goes to a plus, and we are going to integrate this and then find this limit. If this limit is finite, then we are going to say this integral is convergent. If this limit is not finite, then we are going to say this integral is divergent. Number 2, f is continuous everywhere except b at this limit point. Then we are going to write it in terms of limit. We are going to let c goes to b from the left, and we are going to calculate this integral first and then take the limit. If the limit is finite, then this is convergent, otherwise it is divergent. And the third situation could be f could be discontinuous somewhere in between a and b. Let's say it is discontinuous at c. Then we are going to have this piece which is suitable to the part 1, and we have the second piece which is suitable to part 2, and we are going to find their value by using 1 and 2 up here. And we are going to say if this limit and this limit, if they are both finite, then this integral converges. If at least one of them is not finite, then this integral is divergent. This is the improper integral of type 2. This is a nice example. We are going to work on that as well, on such examples as well. Let me give you, since this is summary, I'm just jumping up. Test for convergence and divergence. Sometimes they are going to, you will be given an integral and you're going to be asked to determine whether the integral is convergent, divergent. So there are some tests to do those. The first test is direct comparison test. What you would do is you have two continuous functions f and g on this interval, and g is bigger than f, okay, on this interval. Then we have two situations. If you know that the integral from a to infinity g, g is bigger than f, you know. If this is convergent, then the integral of f is convergent. If integral of f is divergent, then integral of g is divergent as well, because divergent means doesn't have a finite value. So since this is less than that, g is going to be definitely not finite anymore, the integral of it. In the first one, on the other hand, if the integral is finite, then of course the integral of f is going to be finite because f is less than g. Okay, so this makes sense. Okay, we said that as well. And then there are some examples here. See, in this example, they are comparing it with 1 over x squared. We have seen 1 over x to the p before, so we use that. So that's why it was important. Limit comparison test. If you have two functions that are continuous on an interval, then we are going to say we take the limit of the 2 as x approaches to infinity, and if the limit, if this limit L is finite, then these two integrals either both converge or both diverge. Okay. Let me go back to it. Be careful about this limit comparison test, because we are talking about the integral a goes to infinity. So see, x is in here, so we can let x goes to infinity. Be careful. So in the tail, we just check how the functions are behaving, and if their limit is like proportional, like if their ratio is finite limit, then they are gonna both the integrals are gonna act the same way. They both converge, or either both converge or both diverge. Okay, let's continue. Okay, here's another example. See, we are comparing it again 1 over x squared, so it is very common to compare 1 over x to the p. Okay, I'm gonna just skip that. They're asking about the convergence of this. Yeah, let's start on some work with our questions in the homework. So this is the question 13. Perform a test to determine if 0 to pi over 11 dt square root of 3t plus sine 11t converges. The question is, to which integral can this integral be compared to determine whether it converges or diverges? So we are going to just look at all these and then we have to decide, but how are we going to think about this? Let me show you that. Okay, let's look at this question 13. In the question 13, we are going to do comparison. We reviewed the section already. So the integrand here is, I'm going to call it f of t. F of t, I'm going to just look at the integrand. Square root of 3t. T is inside the square root, by the way. Okay, this is important. Sine 11t, yeah? Sine 11t. Very good. Now, I want to recall something. We talked about this a little bit before. The p-test. P-test. Okay. So the integral from 1 to the integral from 1. Okay, so there's this p-test I want to remind you. 1 to infinity 1 over x to the p dx is going to be convergent for p is greater than 1, divergent for p is less than 1. We also have 0 to a number a that's less than infinity. 1 over x to the p dx is going to be, this is just the opposite. It is convergent if p is less than 1. It is divergent if p is greater than 1. Yeah? Because of this 0 here. Here, this happens because of the infinity here, okay? So we are going to make good use of this. You're going to see that this p-test works. You're going to see a lot of examples solved by this p-test. Now, let's focus on this f of t, pardon. So we are going to try to, so it says compare it with either this function, or this function, or this function, or this function. So first thing you're going to do is you should look at these two. Okay, not the other ones. Just look at these two, whether they are going to be useful. But how are you going to compare it? Let me tell you that. Okay. We have to study this f a little bit. Okay, so square root of 3t. Let me erase it. Okay. Square root of 3t. Square root of 3t plus sine. Okay, so we are going to analyze this a little bit. Sine 11t. This is less than or equal to. So I want to make it a little bit bigger. But how am I going to do that? Actually, this is going to be bigger than square root of 3t plus plus 0. Why is that? Because look, between 0 to pi over 11. Okay, let's remember sine. Sine, it has a graph like this. Look at that. Okay, so this is 0 to pi. Yeah, this is pi over 2, and pi over 11 is somewhere here. Okay, pi over 11, and as you would see, it has a positive value. Actually, between 0 and pi over 11, sine is greater than or equal to 0. Okay, on this interval, on 0 to pi over 1, let me do it here. Look, on this interval here, if I can enlarge it a little bit, let's see if I can enlarge. Let's see. Let's go up in here. Okay, this is what I meant. Okay, on this interval 0 to pi over 11, sine is positive, so it is positive means sine of 11t. This is let's write that we are talking about sine of 11t. Yeah. Okay, y is equal to sine of 11t. This graph, and in here it is bigger than 0, so positive. Therefore, if you want to enlarge a ratio like this, if this is greater or equal to 0, in order to enlarge such a ratio fraction, you should take the smallest value of this function. The smallest value is 0, so we put it in 0. So it is true that this is this function here, this function is less than this function. Yeah, this is true. Okay, we can put a big check. This is true. Since it is true, so this f is less than g, and by comparison formula, the integral is going to be less than the integral of this. But the integral here is let's analyze this integral now. Integral of this function. Okay, So what's the integral of this function? Integral of 1 over, I can separate it like this, look, to understand it better, right? So t to the 1 over 2 dt, yeah? This, I'm just integrating it. Let's call it I. This integral is actually finite by p-test. This is 0 to, pi over 11, yeah. This is finite, okay, by p-test. Alright, so here we have the p-test, because p is 1 over 2 here. P is 1 over 2. If you go back to the rule that I told you about, okay, here this is the rule. Between 0 to a, 1 over a is of course less than 0, less than infinity. 1 over x to the p is convergent if p is less than 1. Here in our case it is p is equal to 1 over 2, yeah? It's definitely less than 1, yeah? Alright, so that's it. So it's convergent, so it's the best that we compare this with D. The answer is D because of that, okay? I mean, just a sec. This is the answer. Okay, let me erase the one in the middle here. Okay, this is the answer. And it says, does this converge or diverge? Of course converge, because by comparison this test, since this is finite, it's going to be convergent, so the answer is convergence. Okay, let's see what we have next. Okay, we did this now. Let's go down a little. Okay, next question is number 14. Let's make it a little bit bigger. There's a 15 as well. Let's see. Oh, we went too far. Pardon. Okay, so we are going to be doing this example as well. Use integration, the direct comparison test or the limit comparison test to test the integral for convergence. If more than one method applies, then choose the method you prefer. It says, again, whenever you see such an expression, let's call this integral I, it should remind you that we can use the p-test. The p-test says you compare, what's the integrand here? The integrand here, f of x is equal to 1 over x to the 4 plus 6, yeah? Observe that this is less or equal to 1 over x to the 4. And the p-test says this is on 3 to infinity, yeah? Because of this domain, this is going to be convergent by p-test. Okay, integral of this is convergent. Okay, because of that, then this is convergent. So we are going to say by direct comparison method, so we are comparing this converges because this is true on this interval, yeah? So, and also we know that this is convergent by p-test, yeah, p-test. So the answer is actually A here.